Hi, so in this video we're going to go through practice question 7.3. Now it starts off the same like in practice question 7.2. You are even given the final equation here. Okay, but there's an additional part. So the top part is the dimensional analysis where we come up with this dimensionless expression, and at the bottom is where you calculate the similarities. Okay, when we actually apply the dimensionless equations or dimensionless parameters to figure out the similarities when you have a model and a prototype. Okay, so now let's go through the first part. So the variables controlling the motion of a ship through water are drag force, the speed, the length, the density, the viscosity, and the acceleration. So you might have noticed that it is all the same parameters repeating over and over again. Okay, so the more you practice, the more you write all this down, the more familiar you will get with the all these parameters and their primary dimensions. Okay, so you don't have to waste time figuring out the primary dimensions of all this. Okay, so now let's solve this problem. So here we have the original function. So force or drag force is a function of u. This is the relative speed between the ship and the water. And then the length, of course, this is the length of the ship. We have the density of the water, the viscosity of the water, and we have gravity. Just 1, 2, 3, 4, 5, 6, and equals to 6. Okay, next we determine the number of primary dimensions. So like usual, to do this we have to write down the primary dimensions. Okay, so we have force, velocity, length, rho, mu, and g. So note that sometimes the velocity is written as v, sometimes it's written as u. You might even get other symbols. Sometimes in y direction is written as v, and in the z direction is written as w. So you have to just be aware. How do you know which one to use? In this type of question, it will be given as part of the question here, the speed u. So we know that it is speed. Okay, so now we write the primary dimensions. Force is of course mass over mass times length over t square, kilograms meter per second square, right? Mass times acceleration. U is length over time. Length is of course length. This is density. That would be mass over length square, mass over volume. And then viscosity is kilograms per meter second. So that's mass over length time. Okay, gravity will be length over time square. Alright, so now we get rid of the first term. Of course, we're going to use L. Let's just check while it is simple, and L is also the length of the ship. So in this case, it's most probably going to be a constant. You don't change the length of the ship when you're trying to calculate drag force, right? It's not a variable. So we can fix that. So we get rid of L here by using length. So this will be, it will cancel itself. So for force, it will be force over length, m over square time. This will be u over L, 1 over t. This will be rho L cubed. This will be mass, and this is mu L m over t, and this will be g. We're getting rid of L, so divide by L, 1 over t square. Okay, next let's get rid of m, and we've done this before, very similar in question 7.2. So we can use density times length. Density of water, of course, is a constant, and we've agreed that length is a constant, so we can use this. Okay, so the first one will be force divided by rho L cube. Okay, so here I've made a mistake by writing the L as the dimension symbol L, whereas the parameter L is written as a small letter L. Okay, so it's not a dire mistake, but you have to be careful. Okay, so here we're getting rid of mass. So for the first one, divide by rho L cube. This will be F over rho L to the power of 4. This will not change yet. This doesn't exist. This will cancel itself out. This will be mu L over rho L cube. So mu over rho L square. 1 over T. This will not change. Okay, so next we want to get the final one. So of course here we're getting rid of time, and we check which parameter is repeating. That's how we know which one to choose. So we can, just like the previous one, previous exercise, you know that it's not mu. You don't see mu repeating here. You also don't see gravity repeating here. We don't use this. So we are left with u over L. Okay, actually if you did not have this equation, you tend to choose a simpler one, maybe gravity over L, because gravity is definitely a constant, whereas u probably is not a constant. But you will see that if we chose g over L, we cannot get this version, and therefore this version actually represents existing constants in fluid mechanics, existing numbers. So this is your Reynolds number, for example. So there's a reason why these are chosen. Okay, but like I've said before, I don't expect you to know. So if, let's say, you were not given this final expression and you chose G over L, then you will still get the full marks. Okay, so let's move on. We choose U over L, so this will be, you will for sure get the final term. So just put it, do it on the side if you have to. I'm just going to write the final answer here. Rho U squared L squared. This will be dimensionless. This will not exist. It will cancel itself out. This will be mu over rho U L. Okay, mu over rho U L, because you multiply this with L over U. So the L will cancel. Now you get this. So this of course will be dimensionless. And finally here you G over L times L square over U square. So you have GL over U square, dimensionless. So this is your pi 1, pi 2, pi 3. So you have answered the first part of the question. Of course, don't forget your step 5, okay, which is writing down in this equation form. Okay, pi 1 equals to function of pi 2 and pi 3. Okay, now let's go to the second part of the question, which we haven't done so much. The second part is the similarity. So we have a model boat of a scale 1 to 50. That means the real boat is 50 times bigger than the model. Alright, so this is the model. This is the prototype. Prototype is something that is of real size, ready to go. Okay, model can be of any scale, smaller scale typically. Okay, so a model boat of scale 1 to 50 was measured in a towing tank to have a drag force of 0.27 newtons. So this is the F in the model, when towed at a velocity of 0.91 meters per second. So this is the velocity in the model. Okay, so what will be the velocity of the prototype boat? So here we have to find u of the prototype. So the value of u here, if it's assumed that most drag is not due to friction but to the waves generated, estimate the drag force on the prototype boat. So that is Fp. So here when it says not due to friction, that means it's not due to the viscosity term. Okay, so from that you will see why you can neglect the viscosity term that we have here. Okay. The third one is estimate the power required to propel the boat. So power for the prototype, but then we don't have power here. So power would be an equation of what? So we're going to determine that. Okay, so let's solve for number 1 first, the velocity of the prototype boat. So if we ignore velocity because of this assumption, drag is not due to friction. Okay, so we don't have to use the second term. So to achieve dynamic similarity, you can refer to the first video in the chapter that describes what is dynamic similarity. We will have the first pi, this is the first pi, and the third pi equal in each case, as in equal for the model and the prototype. So we want to find UP. I'm going to use the equation for pi 3, or rather the relation for pi 3, which is GL over U squared. Why use this? Because we need to find the value of U, and we have gravity, of course. Gravity is a constant, and we have the length. So we're not really given the length of the boat, but we know what is the ratio of LM to LP. Okay, so LM to LP is 1 to 50. So no, we don't have the exact measurements, but this is enough. Okay, because you will see that you will put this in an equation like this. GL over U squared for the model equals to GL over U squared for the prototype. Therefore, you don't need the actual value, but you only need the ratio. Okay, so if you rearrange, you can cancel out G because it's a constant. UP over UM, so just rearrange this, equals to square root of LP over LM. Of course, LP over LM is 50. The prototype is 50 times bigger than the model. So there we have UP over UM. So UP equals to UM times 7.07. So UM is given here. Just put that in, and then you get the answer. Meters per second. Okay, now we have U. We have to calculate FP. What is the force, the drag force on the prototype boat? So we can use this equation, the only equation that has force in it. Check that we have density of water, because this experiment was done in water. And then we have U, we already calculated it. We have L, which is this relation. Okay, so the force, put it in this kind of equation. For model equals to for prototype. Rearrange accordingly. You want the force. So put it together. Rearrange everything else. You'll find that you can simplify this. Okay, you can even, if you want to put it in the values, by all means put in the values. Okay, here you can cancel. And UP over UM, here we already have that, and you find that it is related to the length ratio. So this is just simplifying that. Okay, if you want to put U values as what we have here, this is UP, this is UM, you can. You will get the same answer. Okay, so FP equals to 50 to the power of 3 times FM. FM, I think, is given, right? 0.27 newtons, and this is the answer. Okay, so for the last one, estimate the power required to propel the boat. Okay, so what we know about power, basically force times velocity. Okay, you can verify that with the units. So I'm just going to briefly explain that here. Power is in watts or joules per second, and we know that joules is basically energy or work. Okay, and work is force times distance. So work is force times distance divided by work over time. So this is power. Okay, so how do we get force times velocity? Is because d over t is velocity. So we take F, and then d over t is the velocity. In this case, we use the symbol u, so F times u. Alright, so now we want to calculate the power for the prototype. Okay, so the ratio, power for the prototype over power of the model equals to F prototype times U prototype divided by F model times U model. So you will get this relation. Okay, where do we get this relation? F is basically this. The U ratio is basically this. So you just combine that. Or you can, of course, still put the values. Just substitute the actual values that we have. You'll still get the same answer. So power in the prototype will be whatever you get from here times PM. Bring this over. Okay, if PM has to be calculated first. Force times U. So this is FM times UM times this. Okay, 50 to the power of 7 over 2. And you'll get the final answer.